Okay, folks. Dr. Horn is here, but I'm not feeling well, so I'm keeping my camera off. Chapter 7 and chapter 8 is what I'm going to go over now. Hold on, I'm just trying to get my computer to behave itself. Okay, so we're going to go over chapter 7 in our river dynamics book. So we want to talk about channel geometry. We're going to look at it from a 3D view. All right. So you can think about rivers are really three-dimensional. Okay, so they have that plan form, cross-sectional shape, as well as that longitudinal profile. And so we can see that each of those curves, turns, and banks, right? Everything plays a role in the different flow dynamics. So in a plan form, we have meandering, braided, and straight rivers. When we're looking at a longitudinal profile, we're looking at the gradient or the step pool sequences. We take a cross section of the river, we're looking at the variation in shape and flow as far as the sediment goes. When we're looking at velocity, that really has to do with the shape, right? We know that shear zones are really near the bed and the banks, and that we have those secondary flows within the bends of each river. The flow definitely modifies how the channel is shaped, right? Because the flow is what pushes, we just talked about this, velocity of sediment, how it carries it, how it deposits it. And how the channel adjusts back and forth really impacts those flow shapes. Okay. Um, in a river, you have what's called a self-reinforcing feedback loop. And we did get to see that with the Owens River from above. You can see it go back and forth, and a river really wants to wind back and forth. So we have some really cool hydraulic geometry. So there are like a mathematical equation, right, between what a channel dimension is and how much discharge happens. We have two types. We have at a station, okay? So at a spot and then downstream. And so we describe these with what's called a power law equation. So when you're at a station, you're taking width, depth, and velocity, mean velocity, really. You're going to use log plots to show what's called a nonlinear growth. And you'll see variability within the channel based on the substrate, right? Like look, we just talked about vegetation, rock size, sediment size, velocity, etc. So when you have a bigger width, right, it goes slowly, depth increases slowly, but velocity changes and or remains fairly stable unless there's a big change, right, in your slope or something along those lines. When you compare large rivers and small streams, you can see the big difference, right? You can see lithological controls as far as how climate has to do with it and the big changes in those smaller streams. So remember what bankful is, right? So bankful goes all the way up to the riverbanks, okay? So that discharge equals what's called effective discharge. And we just learned about this in the previous chapter. It really causes the most shaping of the channel, right? So you see this in a lot of our geometry studies because we're trying to figure out what actually physically shapes the channel. So the morphological changes, that's what we're looking at. So that's the physical shape, okay? When we're talking about channel geometry, it's just another word for physical shape or what it looks like. The hydraulic geometry is really the statistical flow of those shapes and their relations to the flow in the water. We use it for different stuff, right? If you want to be an engineer, okay, versus an ecologist, that's how we look at things differently. Engineers want to see exactly what happens. We ecologists want to see why it's happening and how it's affecting everything in the whole world. Okay. Engineers are pretty single focused when it comes to stuff like that. We really look at the spatial and temporal variability, right? So what's around it? What season is it? What year is it? That's why we monitor for decades and not just a few days. What you see when the channel changes is really the change in discharge sediment, right? How much is the supply? And then what does the slope look like? We're always looking at the geology underneath, what's the land use around it and the vegetation. So this should all be familiar to you from the previous lecture. And then human influences, right? So we've seen what happens with a dam, with an aqueduct, with a levee, and then what urban landscapes do, right? And so we have a lot of restoration that we need to work on, and we want to look at those impacts. So we really look at observed data and we use it for planning, right? Because we need to see what the river's going to do. We're trying to plan to build around it, use the water from it, etc. And those channels go kind of all over the place, right? It's pretty dynamic. It depends on the flow, it depends on so many things. And so we use these models to try to find the thresholds, right? The river should do this to this point, and then something else will change. That's what I mean by those modeling the thresholds. So you have flow resistant models, and that's the physical analysis, right? Like figuring out exactly what the resistance is going to be until something changes. And then those sediment transport thresholds. So remember, right, each piece of sediment, big or small, has a threshold of how much resistance before the flow pushes it along. That's all that means. And then we have competence and capacity, and all that is analytical models versus numerical models. So I'm not going to make you do this, but if you were to go to grad school, this is what you would do. Everyone really feels like channels evolve on their own. I know when Dr. O'Hara talked about this, she said the river wants to go this way, it wants to go that way. Um, it's trying to move as much sediment as possible with the least amount of energy. So there's all kinds of assumptions, right? So is there a trade-off in evolution of channels? We don't know, right? There's limitations of each theory. So we use what we call steady state assumptions. We assume certain things and we take equations and measure them. We use this a lot for what we call sensitivity analysis. So sensitivity analysis would be applied somewhere like this river can get to bank full based on this amount of precipitation, causing this much erosion and this much sediment deposition before it causes X, Y, and Z issues with the landscape around it. You have to be really careful because, as we know, you can make assumptions, right? And what does that make? Something out of you and me. And then if you look at disturbed systems or human impacted systems, it's really hard to make predictions because once we started messing with things, we change things that we don't even realize. So you have to look at other methods, right? And always check with field data. Always go out and check your field data. We look at cool models and then we use that field data together, making better predictions for management. We want to think about stream design and flood mitigation, right? And different adaptive strategies. So Owens River, again, I'm going to keep harping on this because it's such a big restoration area. You have to think about managing an entire river, right? And that goes miles and miles and miles through all kinds of different vegetation, habitats, different needs, different human impacts. So land use, slope, all the things that we looked at were very interesting, right? So there's a lot to think about when you're making these models. I just talked about this. So channel geometry, obviously this is geology, right? So we're not talking about from today to tomorrow. This is millennial time scales rather. The other thing to think about is if there's been a dam, right? And was the dam taken out or not? And then you can see these stream recoveries. So this is happening in the Northwest, and we are slowly getting some really cool data. If you're interested in that, I can always point you in that direction and show you how to do some cool models. Overall, chapter 7 is pretty short, right? It's mostly just talking about how form and flow work together. Geometry, or the morphology of the river changes with time, okay, and it's variable. And there's lots of different kinds of models to help explain all the different patterns of this. There's not just one way. Here's a couple of questions that you can use to practice for the exam. I'm going to go ahead and open up chapter 8. Let me share my screen again. Okay, so what is channel plan form? All right. It's really the map view or the horizontal pattern of a river. So we're looking at this in 2D now instead of 3D. And we're talking about things like meanders, river braids, and multiple channels. So we want to talk about this because it really influences like how much flooding there is and what the floodplain happens, how much sediment gets distributed. What are the outside environmental conditions? How does that affect all the habitat around it? And then if you're in charge of managing that river, that's a pretty complex thing, right? So you have to know all of these pieces, right? This is part of ecology, part of hydrology. You have to know all of these pieces in order to manage that. So it's a lot of information. So there's a couple major types. We have what are called meandering or sinuous, so single-threaded rivers. We have braided, where you have multiple shifting threads of a river. You have just a straight river, which is really low sinuosity. And then we have anabranching, which is multiple kind of semi-permanent channels that go in and out depending on discharge and incoming. So we have these meandering and braided rivers. Meandering has a really high sinuosity. You see lateral migration, right? Like it kind of spreads out. You'll see those big cut banks and point bars. In a braided river, it's much more unstable, has really wide channels, and touch tons of avulsions, right? So you have this big deposition, right, where you see in the middle, then it'll go off another way and then go off another way. So I know they talked about that in the Owens Valley and how the river just spreads out really flat. And that's why there's that crazy amount of reeds just like growing in that one area that they're trying to manage. Straight rivers are really rare in nature. We really only have straight rivers because we engineered them that way, because engineers like things to go from A to B as fast as possible. Antibranching are, if you can think about it, like separated by little islands, okay? And they're really common when you think in lower areas or in tropical rivers. So, what kinds of controls on the planetform will you see from the environment? All right, so that can affect, it can be affected by rather like vegetation and what we do around it, how much slope there is. Is there valley confinement, right? Is it inside of a valley or can it spread out? What's the sediment supply like? And then what's the grain size? Is it big rocks? Is it clay? How much is going to be suspended? And then what's that discharge magnitude? And then what's the variability on it? Is it seasonal, temporal, right? These are all things that we've learned about. So I want you to try to think about that. And you want to try to control them, right? Who thinks they can control a river here, right? Haha. So in a meandering river, you have a fairly moderate slope and a pretty low sediment low, okay? In a braided river, you have lots of sediment. It's really coarse material and it just depends on the flow because of that material, right? And then in these anabranching, you have very low slopes, right? So you have these big cohesive banks and lots of sediment discharge. That's where you get those little islands from. In meandering rivers, we have what are called really moderate or low energy. You get a lot of fine sediments. You have a lot of cohesive banks that have a ton of vegetation, and there's not a lot of variability in that discharge from those meandering rivers. So for braided rivers, they tend to have a really high sediment supply, um, a lot of flow. So you are in like a flash flood area, you'll be in a glacial valley. There's a lot of low bank cohesion and tons of steep gradients. You can think about maybe where something like that would be. And then of course, straight channels, right? They don't really happen. It's really, really rare that you'll see this, and it's because it's an engineered system. Um, LA River is a great example. It's a huge channelization project. The only time you'll see natural channels is possibly because of tectonic movement and controls, but I can't even think of one offhand that's a natural straight channel. And then we have these cool interbranching ones, right? So the Mississippi, even though it's not, tropical, is a huge interbranching river, as well as you think about the Amazon, right? There's super low gradient, lots of sedimentation, so lots of deposition. Got lots of little islands, and then you see a lot of avulsion and backwater effects, right? That weird grow back movement because the river keeps branching off and kind of becoming its own little weird network. You have multiple channels with lots of cohesion, and then you get these island braided, which are semi-stable islands. And there's a little bit of flow variability, but not very much. So what changes planforms? Climates and hydrologic variability, right? So the amount of water coming through, the land use around it, and whether or not there's deforestation, because what happens when we take away trees, right? We've all learned about the hydrologic cycle. You know how it stabilizes soil. And then, we just learned a ton about the diversions that happen in the LA, for the LA aqueduct, right? And that's that flow regulation, as well as sediment loads. So these are the four main things that change planforms. So you need to know this. And why does that matter? Well, if it changes how much sediment comes down, it can disrupt habitat. It can change, the amount of sediment they need along a beach. You can cause floods, issues with infrastructure, right? And a lot of instability within that channel. So for chapter 8, it's another short one. That's why I'm squeezing them in. So I really want you to pay attention to channel planforms, okay? How does flow, sediment, and the boundary conditions all work together? Remember, there's different types. They each have their own environmental controls, and those external factors can really change and drive transitions. So pay close attention to those key points. Here's a couple questions that you could use to practice for the exam. And that's all I have for tonight.